The study of smart microgrid stability using diesel engine governor and excitation system controllers. Abstract. In recent years, the demand on renewables has been continuously increasing, which is motivated by environmental policies to push for the retirement of fossil fuel power generations and to move towards zero carbon emissions. The driver of enhancing the power system reliability makes it feasible to interconnect conventional grid with renewables. The concept of smart grid has enabled the monitor, control, and automatic dispatch of power flow in today's power network. This paper will review the impact of renewables penetration on conventional grid stability, and also it will introduce some approaches to improve the power system stability. In the last sections of this report, the modeling of diesel engine with governor and excitation system controllers will be described and simulated in smart microgrid case study to evaluate the transient and small signal stabilities. Keywords: smart microgrid, conventional grid, governor, excitation, stability. Introduction. Electrical power generations are strategically located closer to power resources or nearby water sources for the purpose of logistics and cooling respectively. As some of power grids are separated in remote locations, the economic advantage of integrating local grids with national grid could be not a cost-effective solution. However, as the power demand increases and the redundancy of the power supply to the customers is a reliability concern, interconnecting local grids can contribute sustainability to overall power generations and consumptions. In conventional grids, spare generators are held on standby mode to overcome stability issues during peak times and prevent poor power quality and blackouts. In addition, at low power demand during the day, some turbine generators are required to be turned off. One solution to effectively utilize turbine generation is to motivate the change of power consumption behavior by introducing dual tariff with low rate charges, especially when power demand is low at night. There are other approaches that are not affecting the customer behavior, such as introducing power storage systems and renewables. Although the penetration of renewables can supply high clean energy, but there are some engineering designs concerns, such as power electronics harmonics and trading flexibility, of interconnecting renewables with national grid. As the technology advancing, it is possible exchange power information between power generators, storage systems, and customers through IT solutions. Furthermore, the implementation of remote power switching and isolations became smarter and safer at different. Mohamed Abido. Electrical Engineering Department. King Fahd University of Petroleum and Mineral. Dhahran, Saudi Arabia. Power network levels in the generations, transmissions, and distributions. In this paper, the second section will review the impact of renewables penetration on conventional grid. The third section will introduce some approaches to improve the stability in smart microgrid. The fourth section will focus on the modeling of diesel generator governor and excitation system controllers to maintain frequency and voltage at the nominal values. The last section will illustrate a case study where smart microgrid will be simulated in Simulink to evaluate the performance of diesel engine governor and excitation system controllers during transient and small signal stabilities. To review renewables penetration on conventional power grid. In conventional power grid, the power network is designed in hierarchical structure where high voltage power generations transferred through transmission lines into medium or low voltage distribution networks, feeding industrial, commercial and domestic loads. However, the integration of distributed renewables into main grid requires new formation of power grid topology. The distributed generation, DG, along with local loads can be named as microgrid, MG, while the conventional main power grid is called macrogrid. Microgrid can operate mainly into two modes: grid connected to main grid, which allows the power exchanged between the two grids, and islanding mode, as it is isolated from the main grid one. When microgrids connected to main grid, two-way communications need to be established between the grids to enable power flow monitor and control one. The retirement of thermal power generations, such as steam turbines, generators driven by nuclear reactors or diesel engines, and the substitution of renewables power generations can cause power system stability issues due to mainly reduction in power system inertia too. Also, the variation nature of renewable resources is another concern for the power dispatch and system stability during disturbances. 1. 3. Review improvement approaches for smart grid stability. There are several approaches that can overcome the stability concerns with high renewables penetration in the grids. Smart grid concept is introduced with advanced IT technology solutions to monitor and control several aspects of power system in real time, including smart meters, global position system, GPS, phasor data concentrator, PDC, intelligent energy management system, IEMS. 1, 3. Besides to that, the reliability of renewables can be enhanced with the advanced power electronic, such as converters and compensators, to maintain grid synchronism at nominal frequency and voltage, even with the variations of wind and sunlight. 1, 4. To improve the smoothness of power flow and grid stability during load and generation disturbances, energy storage system, S, can guarantee uninterrupted power supply, UPS, with the aid from power electronic. 5. Local diesel generators in the microgrid can also play the role to supplement the deficiencies in renewables by designing governor and VAR controllers. In 6. A robust governor control for small signal and transient stability was achieved through two controllers with the same control structure but different gains. These two controllers are switched to one controller if the power drop is .p 20% of nominal value, and switched to another controller when .p equals 20%. The purpose of small signal, speed droop governor controller, is to maintain the speed and power at steady state within droop characteristic, while transient, vast valving controller, is to maintain system stability during sudden and large disturbances by rapid opening and closing of the valve. 6. In 7, consumer priority assignment units, CPAU, are installed in smart houses which allow customers to decide which selective loads can be shed during the emergency of under-frequency events that required load shedding. 4. Modeling of diesel generator. 4. Transient stability study, to maintain the electrical frequency and voltage of microgrid at nominal values through the governor of diesel generator. The overall diesel generator can be described by three main subsystems. A diesel engine with governor model. The engine converts the thermal energy from fuel ignition to machinal power, where the level of fuel consumption can determine the machine mechanical power, speed/frequency. In 8, the engine is simply represented with first-order system, where the governor, actuator, and controller, electrical box, are represented as third-order and second-order systems respectively, refer to Appendix A. The range of model parameters can be selected as specified in 9. The objective of the governor is to maintain the machine speed/frequency at the nominal value by controlling the of fuel consumption through valve opening and closing. B. Synchronous machine model. The synchronous machine converts the mechanical power from diesel engine to electrical power. The machine can be represented with sixth-order electrical model and second-order mechanical model, refer to Appendix B and C, 10,11,12. C. Excitation system model. One of standardized excitation system is AC1A model in Simulink that is shown in Appendix D. The main purpose of excitation system is to maintain the generator terminal voltage at the nominal value. The parameters for different excitation models can be chosen as per 13. The complete model can be built in Simulink, including diesel generator with governor control, synchronous machine, and excitation system as illustrated in Figure 1. For governor control, there is one measurement required from the machine, which is the electrical speed, while for the excitation system, two measurements required from the machine, which are stator. VK study of smart microgrid. A microgrid configuration. Simplified microgrid shown in Figure 2 was simulated in Simulink, where there are four main electrical power supplies are delivered: PV solar farm, energy storage system, S, diesel generator, and main utility grid, infinite bus. The voltage from the utility grid is stepped down from 13.8 kV to 400 V through three-phase transformer to feed single 400 V AC bus. The rest of power resources and the loads are also connected to the 400 V AC bus. The maximum capacity of S battery bank is 540 kWh, and it is designed to provide the microgrid with a constant 100 kW rated at 400 VAC. The output power of PV solar farm is simplified as sinusoidal waveform that varies between 450 kW and 50 kW, which can be expressed as P equals 200 sin, 2 pft, plus 250 kW, where F equals 1/120 Hz. The diesel generator is rated at 1 MW and in normal operation, it generates 500 kW. In the microgrid, there are two types of loads connected to it: constant load consumes 500 kW, and variable loads which consumes power between 200 to 500 kW. The study will focus on stabilizing the microgrid frequency and the voltage at nominal values, 60 Hz and 400 V, through governor and excitation controllers at the diesel generator side. Several scenarios will be examined for sudden disturbances and gradual variations at the generations and loads when microgrid is in grid-connected and islanding mode. To make the simulation less ideal, a white noise has been superimposed into PV output power. B microgrid simulation results. 3 main scenarios were simulated to evaluate the controller's performance of the diesel engine governor and excitation system as shown in Figure 3. Initially, the microgrid is grid-connected with total generated power from microgrid is 850 kW and the load is 500 kW. So, the excessive power of 350 kW is exported to the utilities. In normal condition, the frequency and voltage were at nominal values of 60 Hz and 400 V respectively. At time t equals 25 seconds, the utility main circuit breaker was opened to study the microgrid response during islanding mode. The frequency and voltage were disturbed due to sudden and significant loss of the utility, and both controllers, diesel generator governor and excitation system, were responded immediately. During frequency transient response, the generated power in the microgrid was higher than the load demand, thus the diesel engine speed was increased up to 60.07 Hz, then it decreased to 59.98 Hz before it recovered back to 60 Hz within 4 seconds. Although, the grid frequency recovery was much slower than the voltage, however the system voltage showed high spike approximately 1.5 kV, which has to be considered in the protection design, for example including surge arresters. The second event occurred at time t equals 50 seconds when extra load of 300 kW was added suddenly, which caused another disturbance to grid. As the load increased, the frequency transient of the machine slowed down to 59.9 Hz, and then speeded up to 60.03 Hz until it settled back to 60 Hz within 5.6 seconds. The last event occurred at time t equals 145 seconds, when battery bank level drained out to 10%. At this battery level, there is no power delivered by S and the lost power was compensated by the diesel engine. It can be observed during the simulation, as output power from PV was varying sinusoidally, this gradual variation was compensated by the diesel engine as well. Figure 3, Microgrid performance with governor and excitation controls. To compare the difference between the response of governor with the controller, in closed loop, and without controller, in open loop, Figure 4 shows the response of diesel engine when the governor is in open loop and the microgrid is grid connected. Although, the frequency can be maintained at 60 Hz at steady state, but there was high oscillation at the initial operation of the diesel engine and it always operated at its maximum capability. Figure 5 show the response of the system during islanding mode, the moment when the microgrid was disconnected at t equals 25 SEC, the frequency becomes unstable. In the other hand, small and gradual disturbances will not impact on frequency stability, for example gradual battery drained out. 6. Conclusion. The paper has reviewed the differences between conventional grid and smart microgrid in terms their topologies, and physical location of power generations and loads. The impacts of renewables penetration on conventional grid were discussed, beside to introducing several approaches to improve the stability of the power network. A case study to maintain a smart microgrid frequency and voltage during transient and small signal stability was achieved in Simulink simulation through the control of local diesel generator governor and excitation system. The controllers showed immediate response to maintain the voltage and frequency at nominal values when sudden and gradual disturbances occurred at the power sources and loads.